Okay, maybe we can get started.
All right.
So thanks everyone for joining the first hybrid systems seminar today. This is a part of a series of 4 seminars that will be taking place this semester. We'll be hearing from several students, postdocs, and faculty from the community. So for today's seminar, I'm very excited to introduce Professor Agung Julius. Professor Julius is a professor in the Department of Electrical, Computer, and Systems Engineering at Rensselaer Polytechnic. He received his bachelor's degree in EE from the Institute Teknologi Bandung in Indonesia in 1998, as well as his master's and doctoral degrees in applied math from the University of Twente in the Netherlands. And before joining Rensselaer, he was also a postdoc at GraspLab at UPenn. Dr. Julius serves as an AE for the IFAC NAHS journal, as well as the IEEE Transactions on Automation, Science, and Engineering. He's also an AE for the IEEE CSS Conference Editorial Board and regularly serves in the program committee of many hybrid systems venues, including HSCC, the Workshop on Hybrid Systems Biology, IEEE Conference on Automation, Science, and Engineering, and the Indian Control Conference. Finally, Dr. Julius has received several awards, including Best Application Paper at URAI, and the finalist for the Best Paper Award at IROS. At Rensselaer, he received a couple of awards, including the School of Engineering Award for Research Excellence and the James M. Tien Early Career Award for Faculty. Finally, Dr. Julius received the NSF Career Award back in 2010. So for the format of today's talk, we'll have around 50 minutes for the talk itself and 10 minutes towards the end for questions. So without further ado, Dr. Julius, the floor is yours.
Thank you, Akash. First of all, I would like to thank you and others for organizing, this program. I think it's a great thing for the young members of our community, and it's my honor and pleasure to be, the first one to give a lecture here. And from now on, it can only goes upwards, right? Before I start with the technical part of my talk, I would like to I don't know if everybody's familiar with the institution that I'm from, so I would like to introduce my institution. So I'm from RPI. It is actually the oldest technical university in North America, as you can see on the screen. We are located in upstate New York. You can see a couple of pictures from our campus there. We have, a number of students, as you can see on the screen. They participate in our educational activities, research, and so on. They have a lot of fun, as you can see on the screen. Troy is a nice, old town in upstate New York, and we're close to many sort of outdoor activities and things that you could enjoy in the city. We have many graduate programs, so any of you who are looking for a graduate program for next year, not necessarily in control systems, could be any of the programs that you see on the screen. Please consider us. We usually get a lot of applications, but we are always hungry for more good applicants for our graduate programs. And if you have friends who are interested, please let them know as well. All right. So moving on to the technical part of this talk, right? So the backdrop of what I want to talk about today is the concept of safety and correctness in systems or in control systems. As you know, autonomous system, control system, they occur everywhere. You see, self-driving cars, you have robots, you have critical infrastructures that have automatic control algorithms in them, and we are interested in safety and correctness in all of those. So when we talk about safety in our community, usually safety is understood in an abstract way, as I have on the screen there. So the notion of safety is that the system state does not enter a certain set of states that we deem unsafe. Right? So if you're driving a car and you're looking at the state of your car, safety means maybe you don't, the state of your car, the position of your car does not overlap with obstacles, which means that you collide into obstacles and so on. Right? If you have airplanes, you don't want, let's say 2 airplanes to get too close to each other and so on. Now, correctness is a little bit more general than that. So it's beyond just not wanting your system state to be in some set. but you want your system to satisfy certain properties. And temporal logic is a framework that a lot of people use to describe, what correctness means for your system. So I have a couple of examples here. I have, a couple of expressions here that.
Sorry, Professor Julius.
Yeah.
Would you mind setting it to presentation mode so it's full screen?
Wait, it is not in presentation mode.
No, we're looking at your PowerPoints right now.
Oh, sorry. Let me see. I'm sharing the wrong screen. Let me stop share. Well, thanks for letting me know. What about now?
Yes, that's perfect. Thank you.
All right. Well, thank you. As I was saying, you're seeing two examples here. There are some expression underneath that are from temporal logic. So if you're not familiar with those yet, don't worry, because I could, let me see. I could cover them and give you sort of the natural language version of the specifications that you see under there. So here you see a specification that says, well, your system starts from initial set of states, and then you want to make sure that within some deadline, the state reaches a goal, while always during that interval avoiding the unsafe set. So here, you have another sort of specification that says, you have to visit two set of states, A and B, within some deadline, but there is some kind of sequencing requirement that you cannot visit B before you visit A, right? So you could see that, there is sort of a flavor of, safety, like what we saw before, but there's also now additional things such as deadline, ordering and so on. So correctness could be a bit, broader than just safety. So in this, get rid of this thing. Right. So in this presentation, I will talk about a number of different aspects or related to safety and correctness. So I'll talk about verification. Let's see, what's it not? Okay, in that order. So I'll talk about verification, which is the activities of proving that the given system model satisfies desired safety or correctness behavior. I'll talk a little bit about control or synthesis, where the idea there is to design a controller or to devise a plan for a system to satisfy a certain behavior. Monitoring is something that is also important, but I think I'm going to skip that. I'm not going to talk about that in this presentation. But I'll talk about inference or induction, which is the idea of, given observation of your system execution, can we describe what we're seeing using the framework of temporal logic that I briefly showed you earlier. All right. Now, if you look at these four topics, I think roughly you could see that the top two are sort of model based, both in continuous and discrete time. So that, basically you work with model with a given model or system. The bottom two are more data driven in the sense that you work with not necessarily a model of the system, but data of observation that you make over the execution of the system. So now I don't know if everybody is familiar with temporal logic. I think this is a tool that a lot of people in our community use. But I think in the interest of getting everybody to a sort of same frame of common knowledge, I have a few slides to explain to you what I mean by temporal logic. There are many different flavors or varieties of temporal logic. I'm showing you on the screen here something that's called signal temporal logic. And it's essentially, the way you want to think about it is a framework where you have logical statements about signals, right? About quantities that evolve over time. the first line here is, what you see here is the syntax with which you could create the logical statement. So let's look at all the ingredients. So the first ingredient here is the Boolean constant true. So this is a symbol that basically means true all the time. It's a tautology, right? And then you have atomic predicate. So that's, think about it as some kind of logical properties that you could describe about the value of your signal. We'll see a couple of examples later. You could have negation. So if you have true with negation, you can also have false, for example. And then you have the Boolean, the usual Boolean operation. So you have and or, and with negation, you could have, all the other classical Boolean logic operations. The new thing that is particular about temporal logic is probably this operator that has the aspect of time in it. So this is an operator that's called until. I'm going to explain to you a bit about that later on, right? Now, the idea of temporal logic is, again, is logical statement over quantities that evolve over time. So essentially, you assign or define truth value for a given trajectory and time, right? So the truth value of a trajectory is a function of time. Like, for example, if you say that, today is raining, right? That statement may be true today and false tomorrow because maybe tomorrow, doesn't rain, something like that. Now, just, again, to give you an example or illustration for the concept, right? So, I have this picture here where on the top you could have a trajectory, and at the bottom you have the truth value of a temporal logic formula or statement about that trajectory. So the truth value of true is always true, regardless of the trajectory and time. The truth value of not true or false is obviously always false for any trajectories. And then the others, you could see more examples, right? So for example, if you see the trajectories that goes like this, so the curve here represents the trajectory, and the rectangles A and B defines a couple of logical predicates. So you could see that the truth value of the predicate that X belongs to this set A is true up to time T2, but false afterward, right? And B is true within T1 and T3, but false otherwise. And then A and B is only true in the intersection, and so on. So you could imagine that you could define, so all kind of Boolean operation for these logical predicates, and you could evaluate them like that. Let's see. Until is a little bit more tricky, right? Essentially, if you have this expression where you have one formula phi1 and phi2, and you connect them with this until operator with a time interval a and b here, basically what it means is that this formula phi1 has to be always true until phi2 is true, and phi2 has to become true in the time interval given by a and b. So if you are at time t, right, so this is what this cartoon is saying, then this expression describes the fact that this phi1 is always true until sometime t prime where phi2 is true, and that t prime has to fall between t plus a and t plus b, right? And I could apply that kind of description on the example that I showed you before, right? So then I could have an expression that says, for example, x belongs to a until x belongs to b, and x belonging to b has to happen at most t time units later, and then I could evaluate this expression, and I could get this kind of truth values, right? Where this is true when t is let's see, so t1 minus capital T, because T1 is when B becomes true in the first time, right? So you could have temporal statements like that. A couple of things that I guess I could just go over this very quickly. There are things that are called syntactic sugar. So what it means is, some kind of definitions of temporal logic, formula that is not in the syntax that I gave you earlier, but it is defined on top of the syntax because it is nice to have and it's easy to use. So one of them is this concept of eventually. So eventually is defined like this, but basically what it means is you look forward in the future and you expect that between t plus a and t plus b, if you are at time t, that this formula phi is satisfied. Okay, and then there's also the always operator, which is basically again looking at the same time interval, but you expect that that formula phi is satisfied for the entire time interval, right? So diamond means eventually, and then this square means always. All right. Now we can go back to the couple of examples that I showed you earlier, and then we could try to read what's going on, right? So if you look at this thing on the left, so this says not unsafe until I reach goal, and then I have to reach goal within t time units, right? So that's essentially the natural language expression that I gave you before. And what about this one? This one says eventually within 2 time units I visit B and not B until I visit A, right? So again, that means I have to eventually visit B, but I cannot visit B until I visit A. So that gives me a deadline of visiting B, but also the constraint about the sequencing of the visits, right? So the two things that I mentioned earlier. Now, of course, now you could imagine that this is a really useful tool. You could use this kind of framework to describe all sort of different properties in many different domains of applications. You could have a statement like this that basically maybe describes the desired behavior of your mobile robot. If the battery is low, then you have to be in base within 10 time units, or some kind of goal for regulation of your power grid. So if the frequency is low, then within some deadline, the frequency returns to some normal range and remain there for some prescribed time intervals and so on, right? So you could use the same framework to express all sort of different interesting behaviors that you want to have for your system. So the first thing that I want to talk about is this concept of verification, right? So somebody gives you a system model and you want to prove that the system described by the model satisfies some desired behavior. So now how do we do that? Okay, this is kind of a busy slide, but basically, I hope, everybody has more or less, some decent understanding of what hybrid systems are. But so this is a cartoon of hybrid systems, right? You can imagine, having a system with multiple modes of dynamics or multiple discrete states. So here they are described by L0, L1, L2, and so on. And within each discrete state, or within each mode, the continuous state dynamics could be different, right? So you get x dot equals f0x here, f1 x over there, f2 over there. And then your execution trajectory is basically this continuous state flowing according to the dynamics until you hit some kind of condition that will make you switch to the different modes and so on, right? And maybe you could even go back to the same mode, but that's essentially the concept of execution. So there are many ways you could prove safety and correctness of hybrid systems. What I want to talk about is something that I and some collaborators did well quite a few years ago now, is which is basically the concept of trajectory-based analysis, right? So what is the idea? Well, you have a set of initial state where your system can start. And so let's talk about safety for now, right? So there's this unsafe set of states that you don't want to visit. And maybe you could run simulation on your system. Maybe you run 2 simulations like that, and your simulations show that you are not unsafe. So which makes you somewhat happy, but maybe not too happy, because 2 simulations only tells you, only gives you these 2 trajectories. But what about the rest, right? So the idea is that, well, if you could somehow compute what I call a robust tube around the trajectories, and I can sort of tell you a bit more about that. But the idea is, this robust tube is such that if I were to perturb the initial state within sort of the beginning of the tube, right, I could guarantee that the resulting trajectory does not stray away from the tube. If I could do that, then essentially with these 2 simulations, I don't only prove safety for 2 initial states, but I have a whole continuum of initial states that now I could prove for safety. So that's the gist of the idea. And this is I guess a similar idea has been also explored and used by many others. So you see a bunch of related sort of concepts that you see on the screen. But the main idea is, again, you have 1 simulation, and you wonder, well, can I get more than just that 1 simulation? And so, well, okay, maybe we could generalize the simulation and say something about the neighboring simulations, right? The resulting simulation from the neighboring initial states. So now I would like to, propose to state that trajectory-based verification is actually a neat idea, right? Because, well, the trajectories you could obtain easily from simulations. It's very, parallelizable. You could generate many simulations in parallel. You don't use any kind of grading or quantization. So in a sense, you don't suffer from the curse of dimensionality. If full verification is costly, you could end up with partial verification. If you don't have the time to run 1 million simulation, maybe you run 500,000 simulation and you get something out of that. Simulation also contains sort of timing information. I will talk about it in a minute. That is crucial for temporal logic properties, right? Now, the cost that you have to pay is that you have to somehow figure out how to ascertain that robust property that I mentioned earlier. So this is, one idea that we used, years ago. And this is certainly not the only ideas how you could get the robust tube, but imagine that you have a dynamical system, so x dot equals f of x, and this is 1 trajectory of this system. X dot is the initial condition or initial state. Now, suppose that I could design, or I could compute a function phi that oh, I'm missing a bracket here. So phi has 2 arguments in the forms of the state. And suppose that I could prove that, phi is non-increasing for any 2, non-increasing in time, but for any 2 trajectories of my system. So what it means is I could guarantee that if I perturb my initial state within some level set of this phi, right? Meaning I pick any other initial state such that the phi of my original x naught and the new x is less than or equal to r, then I could propagate this level set forward, and then I know that all these resulting trajectories will not leave the the tube that I get by propagating this level set forward. Right, so this is kind of like a Lyapunov type of argument, right? So you use phi to measure essentially the distance, or to define the distance between the 2 states. And then if you know that the distance cannot increase, then you could just propagate the ball with respect to this notion of distance forward, and you know that you will never leave that tube. And so if I also show that that tube excludes unsafe, then that means that I could prove that any initial state within this initial ball will result in a safe trajectory. Okay, now you could get this tube. This is not the only way, as I mentioned earlier, to get the tube. So if you look at the literature in our community, any tool that allows you to overbound the forward reachability of this set, you could use it to establish this kind of argument, right? Now, what I want to say also is that the cartoon that I showed you before. So this is showing you how I could use this simulation to guarantee safety, but this is just a sketch to show you that in principle I could use the same to verify the satisfaction of temporal logic formulas. And this is again a sketch of the two ideas. So if I don't care about safety, maybe I care about my trajectory, my state trajectory satisfying some logical predicate that I described using sort of this yellow set over here. Then if I show that my resulting trajectory flows inside this predicate. Now if I draw the level set like so, like sketch here, and I pull it back to the around the initial state, then I could guarantee that all the initial states that are inside this ball will also result in trajectories that eventually satisfy this logical predicate, right? The same thing could be said about timing. If I show that this nominal trajectory, the black one, goes inside the predicate at time t, then if I could create a neighborhood just like that one at time t, where the neighborhood or the ball is completely inside the predicate at time t, and I find another one at time t prime where this neighborhood is completely outside of this logical predicate, then I can guarantee that anywhere I start within this ball, the trajectory is going to satisfy this predicate, and I will also be able to bound the timing of when it satisfies the predicate, right, which is between t prime and t, right? So anywhere I start here, I know that between time t prime and t, I will end up inside this predicate. So I could apply this to verify again not only safety but also correctness as described by temporal logic formula. So maybe in the interest of time, I'll speed it up a little bit. So I just want to show you here that this is one application where we applied this kind of reasoning. We analyzed a model of a power system or a power network in Europe, where the idea is that you have this sort of description or model of the power network. This is inspired by an actual event where a fault in one of the transmission lines results in a cascade of faults that eventually resulted in a blackout, right? So you have a fault here, and then the fault here results in overcurrent in the other lines as well, and results in tripping the other lines and a blackout. We model the whole dynamics as a hybrid system. The dynamics is, this is a lot of details. You don't have to sort of look at all of them, but essentially this is the swing dynamics of the power grid. So you could see that this is generally a nonlinear dynamical system. We also have nonlinear dynamics for the relay and the circuits for each of the lines here. Basically what we wanted to do is to verify if we were to change the operating points of the network, we would avert the cascading failures that resulted in the blackout, right? And so basically with the kind of tools and idea that I described to you earlier, we could verify that, for example, if you were to change the the generation schedule, right? You increase the generation of this one, you decrease that one, you could avoid the cascading failure. If you were to have a quick start energy storage to rebalance power, you could also avoid the cascading failure, right? So you could use it to verify some ideas that, well, if you design your system differently, then you could avoid sort of the unsafe or incorrect behavior, whatever you want to call it, that cascading failure. Moving along to the second topic, now synthesis and control. So here the idea is, you don't already have the full model of your system. There is some control or maybe some plan that you need to figure out. And the question is, how can you figure it out to, so as to satisfy safety and correctness for constraints for your system that are described using, for example, temporal logic formulas that I showed you earlier. Now, one thing is, you could also extend the trajectory-based idea that I showed you before, right? If you, could design a controller that guarantees safety for, a handful of trajectories, you could use the robust tube to enlarge the trajectories, and then you could have something about, a compact set of initial states. So that idea is certainly there. We used that idea in a couple of publications. But I want to talk about something which is a little bit different. So this is, a slight sort of, deflection from the philosophy that I described earlier. Okay. The main idea is that when you have to design a plan or a controlled sequence of your system subject to some temporologic constraints, you can essentially think of this as some kind of optimal control problem, right? Where you have some objective that you want to minimize, whatever it is. Maybe you want to minimize the time of executing your task. You want to minimize energy usage and so on. You have the dynamics of your system, let's say is given by this equation right here. And then you want to satisfy correctness or safety given by some temporal logic constraints. And the idea is that these constraints, now you could think of these as a constraint to this optimization problem, right? So if the dynamics is linear and all the predicates that you have in your temporal logic constraints are polytopes, then this is not just us. There's many papers in our community that have shown that you could actually express this problem as a mixed integer program that you can then solve, right? So I did that with Rensselaer, my former PhD students about 10 years ago. But there's also many others in our community that look at this idea of, well, optimal control with temporal logic constraints. You could cast that as some form of mixed integer program, and then you could solve that. Now, if you wonder, okay, why mixed integer? This is a slide that gives you, I guess, a sketch of the idea, right? So I mentioned that if the logical predicates are polytopes, then, well, that polytopes can always be described by a system of linear equations, like AX less than B, it's like that, right? These red polytopes and these blue polytopes. If I take the intersection of polytopes, then I just stack the equations together. So the result is still polytope, which is, again, a system of linear equations. If I want to take complements or unions, then in general, I cannot do it like this anymore. I cannot stay within the system of linear equations, but I could, if I were to add binary variables, then I could describe the union between this red polytopes and this blue polytopes using this constraint. Okay, and so if you see the form of this constraint, I still have linear constraint here, linear constraint there, linear constraint here. The only thing is that I require this y1 and y2 to be binary. Okay, and this is something that's called a big M formulation for taking complements or unions of polytopes, you could look it up further. But what I'm trying to show you is that this logical operations of taking unions or complements of your predicates, you could describe using mixed integer constraints. So overall, your optimal control problem, this one, you could describe as mixed integer linear program. And so you could solve that. Maybe I'll skip this slide. I have a couple of examples. I'll just give you the other one. So this is one thing that that we did. So you have some temporal logic specifications for a robot to move objects between tables and to avoid collision and so on. So we could solve the problem of designing a plan for the robot arm by casting this kind of constraint in the framework of mixed integer linear program solving. Okay, let's see. Okay, I have a few minutes now. The last part of the discussion today is something that I think is somewhat of a trendy topic. I think a lot of people in our community, or maybe even everywhere else, is looking at the field of AI and machine learning, and seeing all the wonders that are going on in that field. This is so the last part of my presentation has something to do with that, right? And this slide captures the main idea. And the idea is that you could think of temporal logic formulas as a feature that you could use in your machine learning problems. This is an example that I have. So let's say somebody gives you a bunch of time series, right? A bunch of trajectories. And your job is to classify the trajectories into two classes, like the green one and the red one. Now, this is a classical machine learning task. You could design, whatever tool, you want to have, support vector machine, deep neural net, and so on. One criticism about, those type of classifier that you could design is that they're not very interpretable, right? So you design a deep neural network to classify, two sets of trajectories. You may do a great job, but at the end of the day, you don't really know how it works, or you don't really know what truly separates these two trajectories. What I'm saying is that if you could design a temporal logic statement that would separate these two trajectories, meaning maybe you have a temporal logic statement such that these trajectories satisfy that temporal logic statement and these trajectories don't, then again, you have a classifier, but you could actually read the classifier. It's easier to interpret. Okay, and this is not really the only way you could think of like using temporal logic for classifying or describing trajectories. There are a lot of other related work that I put in this box here, right? But the point is, I think what is summarized in this cloud is that if you somehow use temporal logic formula as features in your machine learning task, you end up with something of machine learning framework that is interpretable. So how does it really work, right? So let's zoom into that concept a little bit. So I have a bunch of data, right? Red and green. And let's think of it as a supervised learning problem. So the red and green are the labels that already give you, maybe, red has to be false and green has to be true. And I want to find a model, which is a temporal logic formula that separates, green and red, right? So when I put the green trajectory and I evaluate it using the temporal logic formula, it has to say true. And I evaluate the red one, it has to say false, right? So The truth value M here is a function of the parameters of my formulas and then the data that I provide. And so the generic formulation of the machine learning problem is you want to minimize the parameter, you want to find a parameter that will minimize the loss. The loss being the difference between the label, right, green versus red, and what the formula says, right? So I want, if I put in a green one, I know I want the formula to say true. If I put in the red one, I want the formula to say false, right? And so what about these parameters? So what are the parameters of temporal logic formulas? Well, so if I look at this example of a temporal logic formula, then you could see that, well, okay, so what are the parameters that we have here? So I have two logical predicates, right? The logical predicates I could probably describe using linear inequalities, right? So I have these coefficients of my linear inequalities as the parameters for the logical predicates. I have also the parameters for my temporal operators. And because my data typically come in discrete time, the temporal operators here, the intervals are parameterized by integer value parameters. All right. Now, then I have to subtract the difference between the label and the model prediction. Okay, now, so how do I do that? Because label is binary, right? True or false. The output of this is also true and false. So this is not really a smooth function. So if you think about what we do in machine learning and we try to do, any variation of gradient descent, this is not ideal for that, right? Because your loss function is not smooth. And so for that, we can use this concept of something called the quantitative semantics of temporal logic. So this is quite a busy slide, but I could summarize it with the following idea, that instead of saying that, a formula is true or false, or is satisfied or not satisfied, you want to also be able to quantify how far it is from, how far or how robustly your data satisfy the formula. So if I have, for example, this polytope as my logical predicate, then I could say that if my data point is here, then it's very deep inside the predicate, then it satisfies a lot. Whereas if the data point is over here, close to the boundary, then it doesn't satisfy it. It's satisfied, but not by much, right? So you could quantify the degree of satisfaction. That's what I'm trying to say with this system of quantitative semantics for the temporal logic formula. So if we do that, then essentially this loss function could be made as a smooth function of the parameters, and then essentially you could try to solve this problem as an optimization problem. I just want to show you a couple of examples of what we have done, and this is one of them. So we have some data points obtained from a professional soccer or football match, as described here, right? So we have the XY coordinates of the players from one side, from the home team, de-identified. The question is, can we learn subgroups and the behaviors of the players based on this temporal logic framework? Okay, so I skip all the details and show you the results. So basically, what we have in this work is a framework for temporal logic, where we describe the properties in two layers. So you have the so-called agent properties. So you have temporal logic formula such as this one phi that describes the behavior of an agent or a player. So this one says you have to be in the red zone for some time, and then sometime later you arrive in the yellow zone, right? So all these temporal parameters and the yellow and red polytopes are learned using the framework that I described earlier. So this describes what a player would do, and then at the team level, right? So this is called a census STL. So at the team level, you describe the number of players that satisfies or that are executing the behavior that you describe in the low level. So this behavior is called running back, right? So you were in red, and then sometime later you were in yellow, so you were running back. And then at the group level, you could identify properties that says, for example, if the number of players in subgroup S1 that is running back is greater than 0, right? So somebody in group S1 is running back, then within this many time units, there will be more than one players in subgroup S2 that's also running back, right? So you could describe sort of group, subgroups and behaviors of agents or players within the subgroups. Right. I think I probably am going to skip this in the interest of time. This is another application that I'll just skip that. What I want to say next is the following. So if you look at the temporologic formula and you look at the activities of trying to calculate the satisfaction or the degree of satisfaction of the temporologic formula, it actually has some kind of an interesting structure, right? So this is an example. So let's say we look at this formula that says there's a logical predicate pi, right? And then this segment right here, it says that always in the past, 2 time units or 3 time units, in the past 3 time units, pi is always true, okay? And this is nesting it with another temporal operator that says within the last 4 time units or the previous 4 time units, this property is true, right? So this is saying that, within the last 4 time units, it is true that pi is consistently true for 3 time units, okay? So now suppose that you want to calculate the degree of satisfaction of this formula. So you could have your signal, right? Your trajectory or your x, your signal over here, and you pass it through the function that describes this logical predicate. So if this function is positive, your logical predicate is true. If it's negative, it's not true, and so on. And then you want to look at whether it's consistently true for 3 time units. So basically what you do is you take the minimum, right, of the last 3 time units. So this is, you can think of it as shift registers, or at every time step, your value goes down the register. This operation, again, this is looking at whether in the last 3 time units, this logical predicate is consistently true. It takes the minimum of these 3 values. This one is eventually, so it's looking at whether in the last 4 time units, this statement is true. So then what it does is it looks at this last 4 and it's taking the max, right? So whatever comes out of here is the truth value of this formula given by, the signal that is being fed here. So this looks like a network, right? I have a bunch of operations like this. I can think of this as some kind of weighted network, but this is with some particular kind of weight where, when I actually take this into account, I have a weight 1. When I don't take into account, I don't care, so the weight is 0. So it's some kind of like a, some kind of network, maybe similar to a neural network, but the weight is always 0 and 1, right? So that's the sort of the classical temporal logic. So a few years ago, we started with this question as, maybe we could make this more like a neural network, right? And so basically that led to some ideas where we say, well, okay, if we introduce weight to the framework, so you essentially not have the classical temporal logic anymore, but we make it somewhat soft. You allow the truth value to go not just 0 and 1, but a continuous with continuous values, and you allow to have weights in your logical operations. Then we could actually cast the operation of calculating the truth value of neural network of the truth value of temporal logic formula as a neural network, right? And then you could use deep learning techniques to identify all the parameters. So this is, I think in the community these days, I would say that this is something that's called a neurosymbolic machine learning approach, where yes, you have sort of a neural representation of the model, but also, in this case, each neuron would have some kind of symbolic representation in the form of weighted temporal logic. What you could get with that is that you could speed up your learning task tremendously, as you could see in this table. And this is, I guess, the last slides that I want to show. We also applied it on some biomedical signal processing tasks. So we look at EEG signals to detect epileptic seizures. And so the question is, can we identify a classifier that would allow us to detect or predict seizures? And we want the classifier to be in the format of the weighted temporal logic that I showed you a couple of slides ago. And indeed, we could do that. We published it in this paper that showed that the performance is actually high, comparable to the previously reported methods that are more, black box, right? Our method is based on, again, weighted temporal logic, trained using a deep learning technique in a way that would allow us to describe the decision boundaries between, what you see of the EEG signals of the various channels, and when do you see that the person is going to have seizure. Okay, so that's essentially it. I have, I guess, 5 minutes left in the hour. So just to give you a quick summary, we talk about 3 different activities related to how you could use temporal logics in the analysis, verification, synthesis, and inference of hybrid systems. Thank you.
Thank you for the great talk, Dr. Julius. So if we have any questions from the audience, we can take them now. Maybe before that, I have a question that I can ask. So I think if I understood your talk correctly, you had sort of, you kind of assumed that the STL formula has its particular structure when you're doing this
Yes.
learning procedure. And you do try to learn the quantitative values in the formula, so things like the times on the formulas. Is there maybe like a way that you can use some sort of generative model to try to like learn the structure of the formula and then apply your method to try to learn the values?
Yeah, that's a great question. So I kind of swept that under the rug. So that's a really acute observation. So what I guess this slide will capture the essence of your question. Like what Akash was saying is that, well, I showed you I could parameterize this by A and B, A1, B1, this one by A2, B2, this one by 0 and 5. But the structure itself, like, how do I come up with the structure? So we approach that in 2 different ways. So at first, we have some kind of like a decision tree type of approach that explores all different structure of the formula. So we do this, but then we do this for nodes on the decision tree. And then later on, we also look at, inspired by what folks in machine learning or in deep learning did with what is called differentiable architectural search. So essentially, to summarize it in one sentence, you could have many competing architecture. You give them weight, and then you train your system to optimize the weight of the different architecture, and you sort of force it to be sparse also. So the hope is that at the end of the learning process, you have maybe only one architecture being chosen with a positive weight, and the others would have 0. So that's the other approach. Now you brought up, I think, an excellent point that maybe we could use some kind of generative AI framework to make a guess of the structure, because maybe what the structure should be is something that is quite intuitive for humans. So maybe as a surrogate for humans, you could use generative AI. That is very possible. I haven't looked into that, but I think that's a great idea. One thing that I want to say is that there are people in our community who looked at the use of generative AI to do the reverse. So you start with well, I guess maybe it's even the same. So you start with natural language expression, and you want to translate that to temporal logic statement. And so there's a lot of work being done there as well.
Thank you. It's very interesting work. Oliver, do you have a question as well?
Yeah, I mean, I was thinking about this idea as well, but in the context of stochastic systems. Don't know if you've thought about that as well. Especially there, it's kind of like if you have different trajectories, the question becomes, how does this converge?
Yeah, okay. So we did some work there. I didn't include it in the slides, but I could give you sort of the gist of the idea. And I think Professor Zamani is on the call, and he would be the expert to talk about this. But generally, it's like this, right? So here, what I showed you is that if I start here and I know that all these neighboring trajectories are going to remain within the tube. If the system is stochastic, let's say you have white noise affecting your system, right? You have a stochastic differential equation, for example. Then this notion of stability, right? You could still express that, but with some kind of probabilistic twist on it, right? So you would say that, well, I will not leave the tube with probability 0.99 or something like that. And so you could get some form of probabilistic safety guarantees based on that type of idea, right? You could use stochastic stability type of results to replace the deterministic stability, and you could have that.
Yeah, I understand that part, but I thought you're using these specifications as like a basis in which you're trying to infer a model that predicts if the system satisfies certain specifications. So say you're just interested in safety, right? Can you use a basis of features that are just these kind of symbolic specifications to learn this model? I thought that's what you're using.
So in the last part of the talk, so that part, we're not really talking about model identification, right? Rather, we're trying to figure out what describes a certain group of trajectories, certain group of executions. So in that sense, in the absence of a model, stochastic or the deterministic is not really an aspect that we looked at. Now, of course, when you're trying to do, let me see, where's that picture? So when you're trying to do classification, so where's the picture? Right here, right? So here I gave you in an ideal case where I could classify perfectly. So when the classification is not perfect, I suppose you could attribute that to some kind of uncertainties in your system that gives you the trajectories. So somehow the loss of your classifier is related to the randomness in your system. But we haven't really looked into that.
Okay, thanks.
All right, I think with that, we're pretty much reached the end of the time slot. So thank you very much again, Dr. Julius, for the great presentation. And we look forward to the next 3 sessions of this seminar. So we'll have, I think, 1 a month from now, and then 2 more towards the end of the semester before CDC. So
thank you, Akash, and thank you all for coming.
Yeah, thank you all very much, and we'll see you a month from now.
Thank you. See you then.